Okay, so I suppose I'll start. Welcome to this problem solving and live interaction for the course Experimental Stress Analysis offered by Professor K. Ramesh in Swayam portal. My name is Ganesh Ramaswamy. I'm a PhD scholar working with Professor K. Ramesh, and my co-guide is Professor U. Saravanan from the Civil Engineering Department. I'm pursuing my PhD in the Department of Applied Mechanics at IIT Madras. So we'll go about solving some problems from the contents of week 6 of the course, which has to do with material calibration for photoelastic analysis and miscellaneous topics on that is analysis of photoelastic contours from an processing perspective, as well as the nuances in fringe ordering. So if there are any questions before that, I'd like to take it now. Otherwise, we can go and look at the first problem of the day. Okay, so I take it that there are no questions. So let us look at the first question. So the expression for the principal stress difference sigma 1 minus sigma 2 at the center point of a circular disk under diametral compression is which of the following, given that P is the applied load, D is the diameter of the disk, and H is the thickness. So we know that if we take a disk under diametral compression, so at this point, essentially from theory of elasticity solution, we will be able to see that our origin of the coordinate system is set at that very point. So this is essentially the x and y axis. So there is a standard expression for the we have from theory of elasticity, we have the closed form solution for this, which gives us the stress field in terms of sigma x, sigma y, and tau xy. So from here, if we were to substitute into sigma 1 minus sigma 2, we will get one long expression. This is a function of the function of d, which is the diameter of the disk. This is the diameter of the disk. Diameter of the disk, this is the load applied. And we have the thickness. So we have P, D, H, then our coordinates. I'll just write it as x vector, or let me put it at xy itself. So it will be a function of all these parameters. So if we were to substitute, it is also shown in the lecture, the expression. If we were to substitute x equal to y equal to 0 for center point of the disk, then we will get sigma 1 minus sigma 2 will come out to be 8p by pi dh. So essentially this will be our expression. Now I'll just going one step further. We know that sigma 1 minus sigma 2 is nf sigma by h from stress optics law. So if I were to label this as equation 1 and this as equation 2, so from this I get nf sigma by h is equal to 8p by pi dh, or f sigma for this material is 8p by pi dn. So this is how I get a, just to as a first level analysis for determining the material stress fringe value. So what I would do is essentially I would be loading the disk. So I'm increasing this P. This P I will keep on increasing, and I will note the fringe order. Where will I note it? Because this entire expression has been derived at the center of the disk. So I'll keep on noting N, and then I can just plot P versus N and get the slope from there, which will essentially, using some least squares fit or some type of regression, I can get the slope of that line. Once I have the slope of the best fit line, others are known. It is just a constant times that slope is my F sigma for that material. So this is how I'll calibrate the material. Okay, so just so this happens to be the correct answer for this. So 8p by pi dh is the actual expression. Now there are other ways to make this more statistically stable, where we will just keep this not focused on one point but at multiple points, and then we will define an error function and do least squares regression based on that. So this is just a graphical least squares that will be, you actually work it out by sampling different points so that your results become statistically stable. So I hope that this is clear. If there are any questions, please do ask. Okay, so let us look at the next question. So the number of data points to be considered in the least squares analysis for determining the material stress fringe value should be greater than 1, 2, 3 or 4. So essentially this was developed by Professor Sanford. So for least squares estimation, or rather I should say the sampled squares estimation, so the methodology adopted is that we take a disk again, and then we have our load applied, some load P applied. Now with our origin at the center of the disk, we know the stress field. Let us say that the stress field sigma x, sigma y and tau xy we have substituted in the principal stress difference equation, and we have got the principal stress equation sigma 1 minus sigma 2. Let us say it is given by, as it is mentioned in the lecture also, some xy, some function s. Now we also know that sigma 1 minus sigma 2 is nf sigma by h. So equating these two, we can get that n from here will be s, which is a function of xy, and p and other things, of course. I am leaving that out. Only spatial dependence is shown. Okay. So this will be nothing but n sigma 1 s h by f sigma. So this is one part of it. Now there, for example, if we take polycarbonate sheets, those, because of its manufacturing process, those come with some inbuilt residual stresses. And if you do not account for those residual stresses, that will creep into your calculation and give you a wrong picture about the stress fields that you are trying to study. But it is convenient to obtain the stress, residual stress, where at every point, so that you can subtract that out. What is one convenient way to do that? You take a disk, you assume that there is already residual stress, and for the first level assumption, you take it to be a linear fit with some intercept. Once that happens, along that residual stress, along with your problem induced, that is by applying P, whatever the fringe order comes at that point, both these together form the fringe order that you are actually seeing. Okay, so for residual stresses, we take it that fringe order distribution is some ax plus by plus c. I could have just as easily taken it as a higher order this thing also, but this is the first level assumption that we make. This was propounded by Professor Sanford, and this has been widely followed in the industry for F sigma calibration. Okay, so this is my n residual. So the n total gives me n plus n residual, which gives me s of x comma y upon f sigma plus ax plus by plus c. This is my n total from my theoretical calculations. Okay, that's fine. Yeah, this has gone up. I'll just move this down a little bit. Okay, so we have this expression. Let me just copy this once again. So this is from theory. From theory, I have this expression where the unknowns are f sigma a, b, c. But when we solve for it, naturally, by the very nature of this expression, we will get 1 by f sigma. We just have to take reciprocal of that. So we will treat 1 by f sigma as the unknown instead of f sigma, which doesn't make much of a difference anyway. So once we have this from experiment, we will have n experimental, which is a function of x and y. We know which x and y we are picking. So we will know the fringe order at those points. Now we define an error function for least squares analysis. For this analysis, we will define an error function, error let us say E, or error function is nothing but my n experimental minus n theory, and I'll take the square of that. Why I'm taking the square? Because I don't want positive and negative errors to cancel out. I want the actual error to be preserved. So this is why we do a least squares analysis. So now, since we have 4 unknowns, require 4 equations. So those 4 equations I can naturally get. So because I know the unknowns here, I know these are the unknowns. So essentially I'll be differentiating my error function with respect to each one of them. If I differentiate with respect to f sigma also I will get, but since to make things simple, I will differentiate it with respect to 1 by f sigma. We can even define that as some other term. Dou E by dou A equal to dou E dou A equal to dou E by dou B equal to dou E by dou C equal to 0, and I'll get 4 equations for these 4 unknowns. Solve them simultaneously and I'll get my f sigma. And obtain f sigma A, B, C. Now naturally what we will notice is that in case the sheet is not having much residual stresses, your A, B and C will be very small quantities. and essentially your major output that will come will be from the load that you have applied, which will be representative of F sigma, which will be represented by F sigma. So this is the theory behind getting the a material stress fringe value. So in the linear square least squares approach, uh, the number of data points at least should be greater than or equal to 4, because we take into account our residual birefringence also that exist in the sheet because of some manufacturing process, and this must be done from time to time, from batch to batch. Both these affect our F sigma. So if there are any questions, I'm happy to take them now, or I'll move to the next question. Okay, so I take it that this is clear. All right. So question number 3 says the assertion is that material stress fringe value is a key parameter in photoelastic analysis. Reason: material stress fringe value is the parameter which relates optical phenomena to the stresses. Yes, essentially photoelasticity, we know, is stress induced. It works on stress induced birefringence. So we have a mechanical stimulus and we have an optical response. So how these two are bound together, this is by our stress optic law. So once we take a photograph of some loaded disk, we know sigma 1 minus sigma 2 gives us nf sigma by h. We know h. Sigma 1 minus sigma 2 is what we are trying to calculate at some point. So we can know the fringe order by fringe order numbering. The only thing that scales this difference up is our F sigma. So if our F sigma is not correct, our translation from optical response to our mechanical stimulus will not be correct. So this plays a very key role, and this F sigma depends on, naturally it depends on our wavelength. It also depends on the manufacturing process used. Then time from casting and other processes like annealing, etc. Although that difference is not much. So what will happen is, if we take, suppose we take an epoxy sheet, we cast it at two different times, we will be able to see that over time the F sigma shows some kind of variation. So it is desirable that whichever sheet we are taking, for example, we are taking a sheet here and we are trying to do some experiment by cutting out some specimen out of this. So it is desirable that we reserve some space and take out a disk from that sheet and carry out the F sigma calibration. So even if we have our domain here, even at a later stage, if we were to do the experiment, we can take that same disk, conduct the F sigma experiment, and find out what the actual response at that time and this thing is, so that we are not way off from the results. Although there are ballpark figures for epoxy, the F sigma comes around 12. For polycarbonate, it comes around 8. But in order to do quantitative analysis, we should be sure about what it is. So this is one way to do this calibration. So this is for calibration. This is the polymer sheet, essentially. So the other portions we will cut out. This is our photoelastic. sheet, if I may say. And this is our specimen. So I hope that this is clear. This is why we do this calibration. Hence, yes, it is very important that material stress fringe value is obtained correctly, because that is the only parameter which relates optical phenomena to stresses. So this is the correct explanation. So I hope that this is clear. Okay, so if there are any questions, please ask. So I'll move to the next problem. Yeah, yeah, okay. Can we move, sir? Yeah, okay. And this F sigma calibration becomes all the more important in case of 3D stress freezing. So there we have to go for sample least squares analysis only, as opposed to plotting P by N, because the center shows lot of variation as it is discussed in the lectures also. So, okay, so I'll move on. So the digitization of spatial coordinates X and Y in a fringe pattern is called which of the following? It is called image processing, image sampling, image digitization, and image quantization. So this has to do with uh, actually the digitization of the spatial coordinates, that is to put the spatial coordinates into a grid, is basically called our sampling. Quantization, I will just explain what it is. So essentially, once we have seen, this is basically our type of sensor that we have in our CCD or CMOS cameras. So each of them will be divided into one pixel. So these are nothing but pixels. So picture elements which are color sensitive, which are brightness sensitive. So once we take our model domain into focus and then we divide that into pixels. So this basically implies that we have done sampling. So this process is referred to as image sampling. Once this is done, once we have a particular focus, the aperture and everything is set, and we have sampled. Now what we do is we click an image. So what will happen is that the light that gets absorbed by the sensor, it will give out a voltage. It will release some electrons and it will give out some voltage. So how do we quantify that, the released response by that silicon wafer to intensity data, to voltage data, is our quantization. So essentially measurement of that measurement and conversion of the sensor's response in voltage to intensity data. This is quantization. So essentially, there will be some errors and noise. All these things will creep in, and it also depends on what technology we are using. For example, CCD technology, charged coupled device, as it is uh, spoken about in the lectures also. Those basically have a ray of pixels where once you take a photograph, each and everything will be the charge that is accumulated because of the optical response by the wafer that will be made to move down and it will be read sequentially. So that is one way of technology. Now the latest thing is the technology that we have called CMOS, where each and every pixel itself has its own circuitry and it will give the instantaneous data. So that gives us more benefit in terms of image sampling and quantization. So such technologies exist. Essentially, this is just dealing with the rudiments of image processing because we are trying to do fringe thinning uh, by identifying the fringe features in a in image. Once we are able to do fringe thinning, we know where the fringes are, so we can pick out the points. For example, for F sigma also, we can do least squares analysis, or for complex problems, for example, problems of fracture mechanics, where we have the stress fields in the near vicinity of the crack tip. There we might have to pick the exact fringe points in order to run a least squares analysis to characterize the crack in terms of stress intensity factors. So there all these finds application. Other than this, there are various fields which use image-based image processing, like robotics, even our biometric cameras, biometric sensors that we have. That also uses image-based binarization of the image and subsequent reading. So these find wide applicability. But as for this course, we have discussed it to the extent that it is applicable for our stress analysis point of view. So I take it that this is clear. Okay. So let us look at this question. The given figure P represents the isochromatic fringes obtained in dark field arrangement of a polariscope using monochromatic light source. So what other thing is telling us that it is monochromatic? We have our fringes are black and white. Essentially, it might not be black and white, it might be black and yellow, depending on how the light from the source is. So that's fine. If the only thing is we will not be able to see colored fringes. So wherever our fringes will be black, fringes will be, I shouldn't say black and white. I should just say fringes are black. The other portion is not a fringe. So the light passes through that. So whatever light, uh, the whatever colored light that you are emitting as a monochromatic light source will faithfully get passed on. Okay. If the point P, which is shown here in the figure, is a sink where the fringe order vanishes as the load. Yeah, as the load increases, find the fringe order at point P. So whether it is 0, 1, 2, or you cannot predict with the given information. Exactly, as you answered, the actual prediction of prediction of fringe order at point P cannot be done unless we know at least one fringe order at this point. So with this information, just by knowing, just by knowing that P is a sink, it is not sufficient to predict, to get fringe order at point P. So we can't get it unless we have some more information. So I hope that this is clear. So if there are any questions here, I'd like to take them. Please do ask. Okay, let us look at this question. The given figures represent the theoretically plotted isochromatic fringes. Theoretically plotted isochromatic fringes in dark field of a disk subjected to three compressive radial loads. So what they are saying is we have this. So from symmetry arguments, if we have to have 3 radial loads and the system has to be in equilibrium, it would have to be like that. So we have this, and then we have the fringes developed here. Third option. Yeah, okay. So essentially we are able to see that if we zoom in and see, we will be able to see that fringes emanate from the load point. And here, this point invariably stays. Only thing is, around this point, fringe density changes. But P does not vanish. So essentially, it is not a sink. So we have been given from the problem statement that it is a disk under compression by 3 compressive radial loads. So essentially we know our sources would be existing near the load application points. So it is definitely not a source. I'm sorry, I shouldn't have ticked this. What I meant to say is that it is not a sink. So P is not a sink, not a source or sink. So we see that once we have a point in a domain where our fringe order concentrates, so by increasing load, our fringe order 0 doesn't move anywhere. So which is why the center point is nothing but our fringe order 0. Now what is a singular point? Before that, we must ask the question, what is an isotropic point? So let me just uh, go a little bit about. So these are essentially for fringe ordering. We require certain to understand certain properties of isoclinics and isochromatics. Isoclinics. So isochromatics have, if we look at the properties of isochromatics, these are sources, sinks, and saddle points. Whereas isoclinics have isotropic points and singular points. Now, if we were to define each one of them, sources are basically where fringes originate. Sinks are where fringes vanish. Now, saddle points, as it is called, it will basically have opposing fringe gradients in different directions. For example, this will have different fringe gradients in different directions. So, for example, for a disk, if I take and I apply the load here, and take it that the center point is a saddle point in case of a disk. So how the fringes appear is we will have fringes like that. My fringe order around the boundary is invariably 0 here because it is a free surface and it appears dark when I do the experiment. From theoretical equations also, it supports that my boundary is free except for the load application points. So essentially my fringe gradient is increasing this way and going forward this way. So if I were to draw a horizontal diameter, Along the horizontal diameter, if I were to draw a graph, I would see that I would get something like this, where this is my center point, and this is N, and this is a coordinate along that line, horizontal diameter. So I would see that the gradient is this way. Whereas if I were to draw the vertical diameter, yeah, so when I draw the vertical diameter, I'd be able to see that I get a quite a high fringe value. I'll just draw it symmetrically. I'll just draw it till this point. It will be like that. So this value and this value are the same at that point. So I'm able to see that the gradient basically changes. So as I go towards the top point, my fringe order increases. In which case, this have different fringe gradients in different directions. So when we load it, we'll be able to see the two sets of fringes come, they intersect and then appear to move away from each other in the other direction. So that is what characterizes a saddle point. Now if we look at the properties of isoclinics, so these basically are characterized by isotropic points. Isotropic points are where material behaves like an optically isotropic response. It has optically isotropic response, I should say. So actually there will be no stress induced birefringence in that case. What this will imply is that all directions are principal stress directions. So our fringe order there will be 0. So you would see that all the isoclinics pass through that point because there is no preferred direction for principal stresses to have their orientation. So every plane is a principal plane. So that is what is characterized by n equal to 0. Now there is something peculiar when these isotropic points also fall on the free surface. Those are called singular points. Singular points are nothing but isotropic points on free surfaces. This has some interesting implications that we will look into later. Okay, so this is what is characterized as the fringe becomes denser, 0 doesn't disappear. So this is our 0th fringe order. This is why the center of the disk with 3 compressive loads, we are able to see that it is not a sink. It is basically the fringes are just getting denser. So it is our 0th fringe order there. So are there any questions at this point? Okay, so I take it that this is clear. So let us look at the next question. The appropriate scanning direction in intensity-based methods for fringe skeletonization of fringes which are in the horizontal direction. So essentially what we are having is, yeah. So essentially what we are saying is that we have fringes like that. We are having fringes like that, but the fringes would actually have a center line. I am not in a position to show you intensity variation here. You just take it that intensity varies through the thickness of this fringe. Basically, my center line is the least intensity at center, and it will just increase. So I'll be able to see a band which I cannot discern. So what I need to do is in order for fringe skeletonization. This is nothing but an erosion scheme, essentially. Fringe skeletons. These are nothing but center lines, points of minimum intensity. So why we want to do that? Because if we see fringe as a band and if we were to collect points from that, so we need to know how the fringe actually is. We are not able to discern it with our eyes or with the camera because of limitation of that sensitivity. But nonetheless, there will be one fine line along this fringe where actually sigma 1 minus sigma 2 is being maintained the same. At the other points, it will show some minor variation. So in order to exactly get the points where sigma 1 minus sigma 2 is constant, meaning the isochromatics, we need to first binarize the image and then we could go for some thresholding or some intensity based approach. Intensity based approach essentially is nothing but we have a mask, we have a pixel mask. This is a moving pixel mask which has a if else condition embedded to this mask. So we will essentially make this mask move all over the image. So it will first scan like that and then it will scan like that. So once it scans, it is already embedded with an if else statement based on intensity criteria. What it will do is once it finds that that intensity criteria is met, it will eliminate that point. So what will eventually happen is as scanning progresses, the fringes will keep becoming thin, will erode. So after a point in time, we will be after certain scanning, we will see that our fringes appear to be this way after certain rounds of scanning. So once we finally get through the scanning, just reducing it to one pixel width, then we would be essentially able to see lines. So this will be followed by pixel width lines representing fringe skeletons. So that output will be like that. We'll be able to get 3 lines. Once we get this, we know that these are the actual points where sigma 1 minus sigma 2 is constant. Different constants, of course, needn't be the same. For example, horizontal, these such fringes we see in the case of a pure bending. So if we were to take this to be fringe order 0, then these will be fringe order 1, something to that effect. So in such a case, it is essential that our scanning mask it meets our fringes at perpendicular direction because essentially we need the normal to that fringe to be parallel to the scanning path. In such cases, for fringes which are horizontal in direction, our scanning scheme naturally should be 90 degree. Now this is a luxury. This only happens in certain problems. For example, if it were vertical, then we would go with 0 degree scanning. Now, if it is quite complex, then it implies that either we have to go for different pockets, find out the surface normals, and appropriately scan them so that our scanning scheme is perpendicular. Yes, sir. Any question, Mr. Rajamanna? Yeah. No. Yeah. Yes. Okay. Okay. Opposite means? Ah, okay. I see. Okay. Then I would suggest you once raise that in the forum, because if there is an issue, then we can rectify that. Okay. Yeah. Does the direction of the scanning matter? Yeah, it matters in the sense that, okay, let me explain this. Let us say that we'll just deal with one fringe for the time being, just to make things simple. Let us say I have this as my fringe, and this dark line is the actual single pixel line which represents my actual fringe. So if my fringe at this point, fringe order at that point, very point is 1, then fringe order somewhere at a pixel that is here would be some 1.1, let us say. And this will be some, if it is increasing that way, then this will also have some, let us say this is 0.9. Let the fringe gradient be from top to bottom. Now, if I were to have a pocket of pixels which basically has a if-else statement, what this is doing is we are having a mask like that. So this is my pixel mask. All this is done to find out whether my center point, whether this pixel that we are checking right now, whether it belongs to the fringe or not. This is the whole idea behind our scanning philosophy. So if I were to move it like that, will this give me any use is what we need to understand. For example, if it is moving like this, if it is scanning the fringe like that, so at this point, what it will check is the forward. Uh, Actually, I have made it quite big. It should be something much smaller, because so for example, if it has gone like that, now this mask will check the point that is forward ahead of the point in this direction, this point essentially, that pixel is having some intensity which is less than the previous pixel's intensity. So essentially it will erode it. It will, based on that if else condition that we have provided, it will make it white. So it will remove that from the analysis. Meaning the next step to this, if I were to move this pixel, this thing here, okay, so I'll basically see a small pocket that has been removed from here. So I will not have anything there. So essentially, this is how the scanning works. Now I've just shown this for a simple case. If my fringe is a band, so it will sequentially keep on doing it unless and until we get to one fine line. The next step to this would be it will remove this. So sequentially, as we see, we are able to finally discern the center point, center line of that fringe. The same thing, if I were to do it horizontally, you yourself can see that it will not work. So it will not erode anything essentially. We'll just keep running it in an infinite loop, and we will not be able to achieve fringe skeletonization. This is why fringe direction definitely matters. So the recommendation is that our scanning direction for fringe skeletonization should be preferably along the fringe normal, I would say, along the fringe normal. Now, this is a luxury, as I said, this might not be possible in every case, that you find the fringe normal, which is, tangible to run this. So, in such case, there have been algorithms developed, even our professor has contributed to that. in a very important way. So those algorithms basically have a finite number of scans, and then using some if-else conditions and some conditional operators, you are able to discern what the actual fringes is for generic problems. For problems where your fringes need not necessarily be vertical or horizontal, it might not even have a constant curvature, like it needn't be circle. It might be some general uh, curve. In those cases also, this has been found to work. So have I answered your question, sir? If there are any follow-up questions, you please ask. Is it clear why the scanning direction matters? I hope that it is clear. Okay, so I take it that it is clear. So let us look at the next question. You can just give it a reading. Yeah, you have any follow-up questions there, Aragappan? Mr. Aragappan? Yeah, yeah. That, yeah, that isn't, no, no, that essentially shouldn't matter as such. If you see that in general, you're in graphics, in all of computer graphics, if we take a pixel board, then our origin will invariably be on the top left. So essentially, this will be my x, this will be my y in pixel coordinates. So whenever I put a loop through every pixel, I have to start there. So that is why generally top to bottom you will be seeing. If you were to run the loop from the end to 1 in a negative direction, it will move. So that essentially shouldn't matter. Yeah. Okay. Match the following according to the classification of fringe thinning methods. Fringe thinning method is nothing but our fringe skeletonization only. In the figure. So fringe thinning methods are how to populate this. You just take a look. Yeah, so essentially if we see, one is a binary based method. This does something called thresholding. So when you have an image, let us say a monochromatic image we have, where we have some features here, some features. Uh, I should have drawn it in black. Let me draw it in black. So these are my features. And this has varying intensity also. Now each and every pixel will have some value from 0 to, for example, if you are considering an 8-bit system, it will have from 0 to 255. 0 being pitch black and 255 being white, pure white. So what we can do is, if we were to draw a histogram for this image, for this binary image, it will tell us what is the intensity, what is the distribution of the intensity. For example, 0 to 255, if my histogram is like that, what that implies is most of the pixels have intensity of 125, which happens to be around the center. So generally you will not see this. It will be something very atypical depending on the case under consideration. Based on this, we will pick a threshold value, a threshold intensity, which has lot of research gone into it as to how to optimize the picking of that point. And based on that, if you provide an if-else condition, let us say this is my, let us say at this point I have one intensity I. Based on that, if I threshold this image, meaning whatever is less than I becomes absolute black, whatever is greater than I becomes absolute white. So that becomes a binary image. By making such binary images, we will be able to discern certain features of those images more clearly. Now it depends on the problem in hand as to what we should pick as that threshold value. So it is heuristic. We should have to do a certain hit and trial in order to obtain our thresholded this thing binary based image. Now this has a lot of applications. Even in fringe skeletonization, this has been used, but it is more effective. What has been found that it is more effective to go with intensity based methods rather than binary based methods. Because naturally binary based methods was a natural extension of the same method being applied to other problems. That is why this was adopted to fringe skeletonization also. After which it was found that image intensity based checking provides with a more robust way to get our skeletonization. So A is and intensity based methods again have two ways to go about. One is masking, one is a global, that is the entire screen, entire image, you do it by at once. Others are mask based where you will be having pockets and you will be applying certain different conditions to each and every pocket, which is again heuristic in nature. So intensity based methods. So A is your intensity based method because that has further classifications as global and mask based. Mask based and global methods. Now the scanning which we saw, where we are doing scanning with respect to intensity, and we will be doing it in finite number of directions in order to design the entire fringe skeleton by using if, else, and conditional operators. Those fall under global methods only. So these are intensity based, and this is binary based. Now, all these are in order to obtain our fringe skeletonization. Why we want to obtain that? Because we want to pick points and maybe run least squares analysis or whatever our application may be. For example, for F sigma also we could be using that. Now there is another whole altogether different way to go about called phase shifting techniques. Phase shifting methods, where instead of going from geometry of the fringe features, we will be essentially discerning the isochromatic or isoclinic parameter, meaning delta and theta, delta by 2 pi is n. So delta retardation and theta, the isoclinic parameter, both we will be able to discern by taking multiple images with different configurations of the circular polariscope and do some mathematical manipulation between those images. Once we do that, we will be able to discern what the fringe order and isoclinic angle at each point are. So these techniques are highly matured and stabilized, and these have also been in use for quite a number of years. So this is another way to go about photoelastic analysis, which is called phase shifting techniques. So as it is said in the lecture also, why fringe skeletonization came about is once we switched from conventional photoelasticity where we were only looking for qualitative information, or even if it was quantitative, it was only focused to a point. With developments in digital image processing and other things, so with computer vision, it got developed in a way that we moved to digital photoelasticity where we started focusing on the entire field. Now to do all this for a point is easier. Or now to do it for a set of a million pixels, it would be better to have it computerized. So the natural extension was whatever they were doing manually, whatever photoelasticians were doing manually, they graduated to do that using computer algorithms, which is where this fringe skeletonization and other things came about. Some years later, parallelly, there was extensive research on how to find this without, as an alternative, phase shifting methods came about, where you just need to take 4 to 10 images of the same domain without moving it by only changing the configuration of the quarter wave plates and polarizers in a specific order, and you take those 10 images and then you process them there will be some mathematical processing done for those images, and you will be able to discern with confidence what is the isoclinic and isochromatic parameter at that point. So those are called phase shifting techniques. So I hope that that is clear. So are there any questions at this stage? Okay, so I take it that it is clear. So let us look at the next. Yes, sir. Sorry? No, I've written it down. One can easily discern it. No, A is intensity based, B is binary. Oh, why is that? A is intensity based, A is 2. Ah, A is 2, B is binary based, 4. Yeah, so we are getting D, right? Yeah, C and D are interchanged. No, the main thing is which one had mask based and global based is the actual thing. So even if I were to write it this way, this doesn't change the meaning in any way. So the main thing to discern is global and mask based fall under which category, whether it is intensity based or binary based is the point to understand. Yeah, which is why I avoided marking it. Essentially, it is the concept which we are trying to study rather than this thing. Okay. Okay, so which among the following aspects of photoelastic fringes correspond to the isoclinic fringe field? So we just saw this. Isoclinic fringe field basically has two characteristics. One is an isotropic point and a singular point. So a singular point is nothing but an isotropic point residing on a free surface. So what is the difference between these two? If we if there is nothing special about a singular point, it's just an isotropic point sitting on a free surface, why do we name it this way? Why do we have to have a separate thing? Any idea? So an isotropic point, where we saw that it is a optically the material at that point, even after application of stress, it behaves in an optically isotropic manner, which implies there is no specific preferred direction for sigma 1 minus sigma 2, which implies that sigma 1 equal to sigma 2. All planes are principal planes, which means n equal to 0. So once this is done, what does this tell us? This only tells us that sigma 1 equal to sigma 2. This is all this tells us. Whereas if we have a singular point, this is already by its very definition, it says that it is a isotropic point which sits on a free surface. This implies that n equal to 0, which implies sigma 1 equal to sigma 2. Now on a free surface, what is it that we know? On a free surface, we have free surface implies it is traction free. Let us say there is a point we have. I'll just draw it as a enlarged stress element. So we are looking at some point where our stresses are like this. Now let us say that this is the surface. Okay, rather let me pose it properly. Let us say that I have this problem. And this is a free surface. The top surface of this is free for our purpose of the example. And let us say I draw my stress element there. I know that this top element sigma n and this thing cannot exist. This is what I know at that point. Because shear cannot cross a free boundary, otherwise it would have, let me populate it like this first. This is the most general representation of the stress element. Now, if it is a free surface, if the top surface is free, this implies that this cannot exist. Shear cannot exist because shear cannot cross a free boundary, in which case all my cross shears do not exist. So I'll delete all of them. So they don't exist. And she also, since this is a free surface, my normal stress cannot exist. So essentially it's a traction free surface. So traction can have two components, one is normal and one is tangential. Both are zero. So now if the top stress cannot exist, the bottom stress naturally cannot exist because it is in equilibrium. It has to be in equilibrium. So at best, the stress that can exist is in this direction. Now we know from our understanding of mechanics is if this is a free surface, and this doesn't have any shear, so the orientation of this stress element basically gives us the principal stresses. So if I were to take this to be sigma 1, sigma 2 will be equal to 0. So this is the principal stress orientation itself, the way we have drawn it. Now, so what this tells us is one of the principal stresses is 0. The other principal stress we do not know. Now, if it so happens that this point P also happens to be a singular, also happens to be an isotropic point, we know from the definition of isotropic point is that principal stresses are equal. And if it sits on a free surface, that makes one of the principal stresses 0, which implies the other principal stress is also 0. When can this happen? This can only happen when our stress tensor is also 0. So at singular points, stress tensor is also 0. So this is the speciality of singular point. This is why we name it separately as opposed to our isotropic point, where stress tensor can exist, but essentially there will be no stress vector because it's not sitting on a surface. So is that clear? Any questions? Okay, so I take it that this is clear. This is a subtle thing to understand from our mechanics perspective. Okay, so let us look at the next question. Identify the correct statements. The sign of the boundary stresses changes when it crosses a singular point. Yes, because we will be seeing that even from a problem of a ring that has been shown in the lecture, we generally see that around a singular point, between two singular points or between a singular point and an isotropic point, our orientation in which when we rotate the crossed polarizer analyzer combination, the orientation in which the direction in which our rotation of isoclinics take place, it gets reversed. So essentially we cannot cross from one point to the other without encountering 0, which is why this holds true, that the sign of the boundary stresses changes when it crosses our singular point. Fringe order at an isotropic point is 0. Yes. Yes. Essentially n is 0, which implies sigma 1 is equal to sigma 2. But it does not say that stress tensor is 0. That only holds in case of a singular point. So the load application point are not considered isotropic points. Yes, if you see our ring problem, it has been shown in the lecture also in detail. So the candidates essentially for isotropic points would be many. We will have them here, then we will have 2 isotropic points here, and then 4 here, and then 4 of them here. But the top and bottom one happen to be the load application point where you again see that all the isoclinics appear to meet. This is because of our stress concentration at that point. We cannot discern anything much about it. So these two are essentially excluded from being defined as isotropic points. So we do not include them in the list of isotropic points. So at isotropic point, the loaded polymer behaves like an optically isotropic material. Yes, there is no preferred direction of stress induced by refringence because n is 0. So this also holds true. And fringe order there is 0, which we saw. So stress tensor at a singular point is 0, which we just saw. That a singular point is an isotropic point which sits on a free surface. Free surface implies that whatever stress element that you draw that is having one of the normals perpendicular to that free surface, that orientation is the principal stress orientation. And the principal stresses that you mark at that orientation are indeed the actual principal stresses. Now, by virtue of that being an isotropic point, it implies that sigma 1 equal to sigma 2. If sigma 1 or sigma 2 is 0 by our arguments of a free surface, then the other principal stress also goes to 0. This is only possible traction being 0 at a free surface and sigma 1 is equal to sigma 2 can only be resolved by our stress tensor being 0. So stress tensor is also 0. So essentially all statements are correct in this case. So if there are any questions, please ask. Excuse me. Okay, so I take it that this is clear. Okay. So based on this understanding alone and seeing the isoclinics, we are supposed to answer this question. Figure 1 shows the dark field isochromatics plotted in case of a crack subjected to mixed mode loading. The crack indicated as a red line. So this is essentially a crack. So what we are having is, we are having a domain where we are having a crack and this is loaded by some external agency. And this is the crack tip here. And these are the type of fringes that we are getting from when we see it in a circular polariscope. And figure 2 indicates the isoclinics plotted. Now, it must be noted that there is no arrangement of plane polariscope that can give you this total fringe, this total output at once. So how this has been arrived at is basically our polarizer analyzer cross combinations has been basically rotated in steps of some does this give? Yeah, 10, 20, 30, right? So the difference is 10 degree. So our figure 2 has been arrived at based on keeping the analyzer polarizer combination crossed, keeping it at 0, 10, 20, 30 and going like that till 90. Why only 90? Because principal stress principal planes are they have a difference of 90 degrees. So even if I go to 110 or 10, it is one and the same. So this has been arrived at by post-processing the isoclinic information. What does this tell us? This tells us some interesting points. We are able to see these points. So these points are where all the isoclinics are meeting. So what does that imply? That these are isotropic points. So if I were to mark those I'm sorry. Just a minute. Yeah, I don't know. Thing hung up and it disappeared. Okay. So essentially, if I were to translate, it is these are these points. I'll highlight them in this color. So one is this, the other one is this, and the other one is here. Okay. So now that we have identified the isotropic points, what do we know about isotropic points? We know that n equal to 0, which implies sigma 1 equal to sigma 2. So now they have asked what is the fringe order at point A, is what they have asked. N at A equal to what? Now there we need to reread the question. These are dark field isochromatics. Now from our knowledge of dark field isochromatics, we know that have I sine square delta by 2. Now when will this be 0? When delta will be in integers, 0, 1, 2, and so on. So we know that the dark field isochromatics has only integer fringe orders. And isotropic points we have, so this is 0. So the fringe order at this point is 0, fringe order at this point is 0, and fringe order at this point is also 0. Now we are moving towards the crack tip, and we are able to see that our fringes are getting denser and our crack tip has very high stresses. So naturally my fringe gradient direction is this way, increasing that way. So if this is 0, then what is this fringe order? This fringe that is coming, this is n equal to the next integer that I see in the gradient direction after identifying my 0th fringe order. So this is n equal to 1. So after that again we go, then we have this fringe that is coming. So this is n equal to 2. So all the points at that line represent n equal to 2. Then this is 3, 4, 5, 6. Beyond a point we will not be able to discern it because the fringe gradient is so high that the fringes are so closely spaced that it will not be you will not be able to discern it unless you go for very special cameras or very close to the crack tip, zoom in very close to the crack tip. Even at that point there is a limit up to which you can discern it. Okay, so we have arrived at this fringe order equal to n equal to 2. So essentially our fringe order at point A is 2. Now what is the next question that is asked? Fringe order at point B. Now where is point B? Point B is over here. So we know if this is 1, we can see that this is one fringe. We are able to see that this is one fringe. Then the second fringe is going something like that. It would have merged here if it was loaded a little differently, but the pattern still holds. So my fringe gradient direction is like that. So if this is 0, then this is my first fringe order. This is second. This is third. This is fourth, fifth, sixth, and so on. That is how I will count. So essentially I can see that my point B lies on the first fringe order. So my fringe order for point B is 1. So what were the things that we required in order to do this, finding this out? Knowledge of isotropic points, which we got from isoclinic data. So we know that it is dark field isochromatics. which told us that fringes are integers. Isotropic point has helped us to identify the zeroth fringe order. Problem. Problem mechanics. We know that crack tip is highly stressed. Now, if crack tip is highly stressed, sigma x, sigma y is very high. So naturally, sigma x, sigma y, tau xy is very high. Naturally, sigma 1 minus sigma 2 is also be very high, which implies that my fringe order at that point will be quite high. Yes, sir. Problem, no, I'm saying what did we, that is, I'm trying to reason out what all information we wanted to solve this question. One was that by from isoclinic data, we were able to identify the isoclinic points, which gave us the fringe order to be 0. Secondly, it was given that this is the information given in the question says that it is dark field isochromatic, which tells me that each and every fringe is different from the other by one integer. So essentially, n is in integers that it has given. If it was a bright field image, then my fringe orders would have been having, it will start from 0.5, 1.5 like that. So these are 0, 1, 2. Third is, how did we arrive at the fringe gradient direction from the mechanics of the problem? What this problem is it is saying that there is a crack tip which is highly stressed. So once we know the fringe order where it is 0 and we move towards the crack tip, naturally my fringe order has to increase. So the identification of the problem mechanics tells me that the fringe gradient should be moving from the isotropic point to the crack tip in increasing direction. Is it clear, sir? Okay. Yeah. So I should have framed this better. I would rather say knowledge of the problem. Knowledge of the mechanics behind the problem. Okay, so crack tip is highly stressed. So this helped us identify fringe gradient direction. Once we have fringe order at one point and we know how the fringes are to be labeled, meaning integers or half integers or whatever, and we know the fringe gradient direction, we can easily do the numbering. The underlying assumption is that this is a continuous body. Essentially, we are dealing with continuum mechanics. So this is a continuous body. There cannot be sudden jumps. So essentially, it will only vary like that. How we can see that further? We know that, for example, if I were to take, let us say this is 2. So I know that this is fringe order 3. This is n equal to 3. Now when I stress, if I were to draw a line, let me take a yellow line here. If I were to draw that line, now from my understanding of continuum mechanics, I know that somewhere midway between these lines, n has to be somewhere between 2 and 3 only. It cannot be 7 or 8. Why? Because of our stress being a continuous function inside the body, which we are essentially analyzing with continuum mechanics. This is why will be somewhere around 2.5 or however the gradient is, but it will definitely belong in the domain of 2 and 3, not somewhere outside. Okay. So are there any questions based on this, what we have discussed? No. Okay. So I take it that it is clear. All right. So let us move to this last question that we have. Figure 1 gives the isochromatics obtained in the case of a ring under diametral compression as the applied load increases. So essentially we have applied P here and we have applied P here and P increases. So what all we are able to see here from figure 1? Okay. Figure 2 represents isoclinics plotted at intervals of 10. As I said, it cannot be obtained from one single configuration. You will have to essentially take steps of 10 and take images and then post process them in order to get the whole field isochromatics, whole field isoclinics. So this is the all isoclinics, and this is isochromatic for some point, for some load, for some load P. And we have been asked to identify what these points are. Okay. And we have to report our answers in one particular format, answer the questions in the alphabetical order without. So I will leave that to the technical aspect to it. Mainly, we are interested in understanding how to identify the features. So once we identify it, reporting is a trivial thing. How to report, we can always do that. Which are the isotropic points here? So for isotropic points, what is the condition? For isotropic points, we have to have all isoclinics should pass through that point. Okay, so if we were to, there was some n equal to 0, exactly. For isotropic points, n equal to 0. But physically, that is n equal to 0 is our conclusion. Physical observation, we see that all the isoclinics have to meet at a point. So one is causation, one is the effect kind of thing. Okay, so let us identify with yellow what are the points, what are the candidates for isotropic points. We see that one is here, then one is here. Then we are able to see that isoclinics appear to meet here. Then since this is an axisymmetric problem, naturally everywhere it will happen the same way. Invariant of theta. For the moment, I will consider this to be the candidate and then remove it because this is the load application point. Let me zoom in a little. What else is there? Are there any other points for being named isoclinics, isotropic? I'm able to see if I essentially note this point here. If I take note of this point, I'm able to see that here also all isoclinics seem to be emerging. Only difference is if I were to take, instead of steps of 10, if I were to take steps of 1, then I will be having dense lines here. Dense lines all meeting at this point. So essentially this is also an isotropic point. Here also my isoclinics meet. So once we have identified one from the axisymmetric nature of the problem, we can know that it exists at other these places as well. Okay, so Are there any other points where we can see the isoclinics meet? Okay, it takes a little bit of closer look. So you can, if you require more time, you can perhaps, when I post this, you can just analyze it, zoom in and analyze it separately. And if you are not convinced, you can bring them up in the next session. Okay, so I have 1, 2, 2 and 4, 6, 7, 8, 8 and 4, 12 candidates. But we know that load application point cannot be termed a isotropic point. So essentially we are left with 10 candidates. Which are the isotropic points here? If I just translate it to the right figure, we have B, then I have Q, then I have B, I have Q, then I have C, then E, U, F. A and B are the load application points. Then on the inner surface I have H, J, L, N. So these are all of my 10 isotropic points that I have. So we need to number them in one particular way, that is arrange them in one particular way as it is asked in the question and report it. So I will not be doing that. That can be done by anyone. Okay, so let us look at the next question. What are the singular points? Now we know that the requirement, what is the blue and black? Is it clockwise, anti-clockwise? Yeah, good question. I'll just explain that. Okay, let me go to the previous question to explain this. This is a good question. I was expecting someone would raise it. Why these are blue and black? Essentially, we know that theta p, from theory, what do we know about theta p? Tan 2 theta p is, sorry, let me, tan 2 theta p is 2 tau xy by sigma x minus sigma y. So theta p you can only get by taking inverse tan function. So inverse trigonometric functions are essentially multi-valued. So these can also hold if your sigma 1, that principal plane direction is 45, or it is 45 plus pi. So in both the cases, tan inverse would give you the same ratio or the same answer. So essentially, you need to do some unwrapping in order to arrive at, because physically, conventionally, when you do, it is quite simple for a simple problem. But if you have to code it and do it digitally, then this tan inverse creates problems. So essentially, what you will get here is the domain will be restricted, which are called wrapped isoclinics. So you will have to unwrap them in order to get them from 0 to pi by 2, or in the actual range of the theta p, rather than having it in a minimum range. So this creates some problem. This is why there are some algorithms which again have a mask-based scanning scheme where they will be removing these ambiguities. These are essentially called ambiguities. And these lead to, when you in phase shifting techniques, when you use this to discern the isochromatic data, that will lead to something called inconsistency. There will be a sudden jump. For example, if you have one point where isoclinic angle is reducing 10, 5, 4, when you go to 0, you expect there will be a pi jump. Suddenly it will start from 90, 91, 92, like that. So that jump comes because pi tan inverse theta, tan inverse of x is a multi-valued function. So in order to remove all that, it has been mentioned that sigma 1, all the black fringes that you see, isoclinic fringes that you see, pertain to sigma 1 principal stress direction. And all the blue ones that you see pertain to sigma 2. So is it clear, sir? It's a valid and good question that you have asked. Yeah, okay then. So the same, because the same software we see here, P-scope is what has been used. So the same software was used to design this also. So black essentially represents the direction, constant directions of sigma 1, and blue represents those for sigma 2. Okay, good. So now let us look at what are singular points. We saw these are isotropic points on a free surface. So out of all the 10 that we have identified, we just need to rule out the isotropic points that are not on the free surface. Which are those? We can see that these two, Q and U, they essentially are zeroth fringe orders that are lying somewhere inside the domain. Except for that, all others are lying on the surface, which is not loaded, which is free of any traction. So these are singular points. So essentially it is the same, except we need to remove, which were the alphabets that we need to remove, Q and U, because these are internal points. So Q will not come and U will not come. Rest everything is representing singular points. So what is special about singular points here? Stress tensor is also 0. Stress tensor is also 0. What are the sources? Source, we saw that the fringes basically emanate out of them. So if we see, actually it is the animation is shown clearly in the lecture. But if we see that sources basically are points from where the fringes are emanating. So the load points are definitely sources. So we have these. Let me perhaps take this one. So we have source here, then we have source here. Then I'm able to see from the animation, if you notice, these points will also act as sources from where fringes emanate out. What else is there? Do we have any sources on the surface? Anywhere else do we see a source? So this we know is an isotropic point. These are singular points. The fringes come out from here and the fringe density increases. The point doesn't disappear because it's not a sink, it is an isotropic point. So the fringe density essentially starts becoming very high. The density becomes very high. There are more number of fringes. Essentially, when we load it like this, so the fringes come out of these points, then they come out of these points, then these. So essentially, what I will be able to see here is, in case of a ring, my fringes comes from here, goes into the sink, goes into, yeah, fringes emanate from here, they emanate from here, and they emanate from the load application point. So towards the end, I will also try to include that animation, but it is anyway shown in the lecture in detail. So you can just have a detailed look at it as to where these sources are, from where it is emanating. Once we have paid enough attention to this problem, why this problem was chosen is because this has features, this has all the features that we are trying to discuss in a single problem. So once we have a grip of this, then we can go for some generic problem, such as the one we saw with a crack, where only certain features were required in order for us to arrive at what the fringe order at A and B was. So others would preferably be only a subset of these. But in order to get the grip of all the points together, this is a very nice problem which illustrates all of them. So essentially sources are, I'll try to highlight that with some other color. A, then I have D, then I have G, I, K, M. So these are my sources in the problem. A, D, I, K, M, G. Okay, so A, D, I, K, M, G. So these are my sources. What are the sinks? So I'm able to see that when you see the animation, D and S. Where is D? D, we have already said it is a source. Right? Yeah, I suppose you meant this point. Actually, this is O. Yeah, that's fine. So you've identified it correctly. There are two sources, and midway, the fringes start vanishing there. And we only saw a close-up of this when we saw in one of the questions earlier, where we were asked if we are able to discern what the fringe order is. We can't do that because it is a sink, and we do not know any fringe order of any other point over there. So essentially, we have our sinks at O and D. Exactly. O and D. Okay. So identify the saddle points marked in figure 3. So I have messed up figure 3 a little. I'll just try to clean it up 1 minute so that we can identify things out of that. So yeah. So saddle points are characterized by are characterized by different gradients in different directions. Now essentially here we do not know how it is changing. So if we were to look at the animation, what a saddle point would essentially be like is if this happens to be our point of interest and we have two. For load case 1, if these are the fringes that we observe, as we increase the load, what would happen is these will merge. So this is a characteristic of a saddle point. I'll just take this out and try to explain it. So for a saddle point, for P equal to P1, now when I increase the load, what would essentially happen is these would merge. These would have merged like this for P equal to P2. Then when I further increase the load, these would have gone apart like that. So this is P equal to P3. So essentially, if I were to see this, two fringes will come, meet and separate out. So the merging and separating out, these actions we can see as we increase the load. Increase or decrease, whatever the case may be. If I were to decrease, it will go in the opposite direction. So uh, these are how saddle points behave. So essentially, we have two opposing gradients. Fringe order at the load application point. Will the fringe order at the point of load application be the maximum? Yeah, I'll just come to that. It's an interesting question. I'll elaborate a little bit on that. So first, if we were to identify the saddle points, essentially you would see that there will be many saddle points here, but a couple of them have been identified here already. So if I were to take V, see these are the fringes that I see. Once I increase the load, this fringe would have moved here and this will become like this. So that is why V is a saddle point. I hope that you're able to appreciate it. So P, R, T and V are essentially the saddle points in this problem. P, R, T and V. Between N and G. N and G. Yes, exactly. These are also saddle points. So by the axisymmetric nature, here also there are saddle points. So there will be many saddle points. So the idea was the question asked that we have to report the saddle points out of which are marked. But exactly your observation is good that you're able to see that these are also saddle points. There'll be some more. Okay, coming to your question of whether the fringe order will be maximum at the load application point. See, if I take a disk and I load it like that, at this zone, my fringe order, I will not be able to discern it whether how my fringe gradient is. If I were to zoom in at that point, so because our point load is essentially an abstraction, there is nothing called a point load anywhere. So what we see is even if we apply a point load, it has an elliptical distribution like this, with the maximum load, maximum pressure getting applied at the middle, and it dies down within a span of say 2a, where a is nothing but the semi-contact length. This comes from Hertz's theory. So in such a case, what we will be able to see is the fringes would look something like that. In which case, a point that is somewhat below the load application point acts as the source of the fringes coming out. So this essentially represents the point of maximum stress, not the load application point. Now, if I make my material more and more rigid, my A will keep on coming down and this I will keep on shifting to the surface, but it will still be somewhat below. In an ideal case, in a theoretical case, with uh, I can apply a point load and my point of application will have the maximum fringe order, but that does not convey, that does not replicate a real life scenario because all bodies are deformable. So I hope that this is clear. So essentially, this goes with the abstraction point of load application having maximum fringe order goes hand in hand with the abstraction that, yes, hand in hand with the abstraction as point loads and somewhat rigid body idealization, that there is no deformation because when we apply a load, there will be some deformation. So even if we apply a point load, it will be get distributed over a finite area. So these things are abstractions. These are only holding in ideal cases. Is it infinite? Yes, it will shoot up. In the ideal case, it will shoot up. But if you see that material also has some limit up to which it can take, beyond which it will start yielding. So essentially, you cannot have metal being loaded up to the point of infinity because your stresses will reach a certain point where it will start yielding. So there, our theories will start falling apart, because of which we need new theories to understand it. Yeah, all right. So I hope that this is clear. Other than this, I've covered all the questions now. So if there are any general questions, otherwise, I'm happy to take them. Otherwise, I'll try to call it a day. So I hope in this section we have discussed how to do fringe ordering, then fringe thinning methodologies, which are parallel to methods like phase shifting in order to do some photoelastic analysis. And then, of course, we saw in detail how we have to calibrate specimens, how we can make it statistically stable, one-point calibration and multi-point calibrations. So if there are any questions based on these topics which we discussed, I'm happy to take them. Will a fringe be formed if the body doesn't deform as a result of stress accumulation? Okay, so if a body doesn't deform, you are essentially saying that we are considering that to be a rigid body. In rigid body, whatever load we apply, it will get translated into displacements directly. So a rigid body cannot have any stress inside of it because it doesn't fall into the purview of deformable bodies. In such a case, stress and stress accumulation don't mean anything. But this is just for first level analysis. All bodies are deformable. So if a body is applied with a load, it will definitely deform. Based on its optical response, it will show some stresses. Is it clear, sir? Yeah, okay. Yeah, Mr. Rajamanar, you had any question? Okay. Yeah, yeah. Okay. Which point? One minute. Let me just try to understand what you're trying to ask. We take two circular discs of different materials but applied with the same load. Okay. Yeah. So which of the quantities, let us say that these are loaded like that. So if this is having a stiffness of E1 and this is having a stiffness of E2, so naturally its deformation will be, if we are applying it, subjecting it to the same load P, then naturally if E1, considering the case that E1 is greater than E2, deformation of E1, deformation of 1 will be less than deformation of 2. So if displacements are not the same, naturally stresses, strains won't be equal, but stresses would be equal. Why? Because under the plane stress assumption, this goes hand in hand with the plane stress assumption that we are having stresses only in that plane. The if you see the compatibility conditions recast into equilibrium equations, they are independent of the stress field, independent of the material parameters, which is why stresses would be same in both these cases. So what this implies is if you take a thin disc made of plastic and thin disc made of metal, if you subject it to the same load, the stresses would be same in both the cases. But strains will, sorry, yes, stress distribution will be the same in both the cases, but strains won't be the same. Yeah. Okay. So okay. So if there are no other questions, then I'd like to call it a day. Yeah. Sixth question. Yeah. Any questions here? I'll anyway be posting this PDF so you can see it from there. But other than that, are there any questions that you have regarding this particular question? Oh, okay, okay, fine, fine. Okay. So other than that, if there are no questions, I'll call it a day. Thank you for attending. Okay, thanks. So I'll end the meet.